Hey everyone, welcome back to the Protocol Labs Research Seminar Series. Our speaker today is Dr. Andrew Critch. Andrew is currently a full-time research scientist in the EECS department at UC Berkeley at Stuart Russell's Center for Human Compatible AI. He earned his PhD in mathematics at UC Berkeley, studying applications of algebraic geometry to machine learning models. During that time, he co-founded the Center for Applied Rationality and the Summer Program on Applied Rationality and Cognition. His current research interests include logical uncertainty, open source game theory, and avoiding arms race dynamics between nations and companies in AI development. Andrew, super excited to have you. I will let you take it from here.
Jonathan, thanks so much. It's great to be here. I'm excited to talk to you guys about this because I think I've done this work mainly from a theoretical perspective, and I'm constantly working to look more at what are the present day and near term applications of these ideas. So I'm excited to have questions about it, and I want to tell everybody, just pipe up if you have questions. This presentation is it's somewhat generic, and so the way it's going to be customized to you is you're going to ask questions in the middle of it to ground it in what your interests are and what you're curious about. So please just pipe up. Of course, you can, if you're shy to pipe up, feel free to put things in the chat too. But I don't mind at all being interrupted in the middle. So the talk's called Open Source Game Theory is Weird because that is a true statement. And I'm hoping that by the end of this talk, it'll be a true statement that you believe. I think a lot about societal scale risks from AI. I'm kind of a generalist in that domain, but my specialty is, as Jonathan mentioned, thinking about logical uncertainty or bounded rationality, which is to say, what happens when a machine with a limited amount of computing tries to answer a question that is technically fully answerable given the information that it has, but it just hasn't had time or space to think about that question long enough to answer it. And I also think about negotiation protocols. So it's natural for me to think about negotiation among agents that have bounded computational resources. I'm guessing everyone here has heard of the prisoner's dilemma, but in case you haven't, the way I usually formalize the prisoner's dilemma is to think of there's two actions, cooperation and defection, that each of two people can take. And you can think of each person as having a bank balance of $2 each by default. And the defection action, all that does is it reaches over and destroys the other person's bank balance of $2 and gets $1 for yourself. So you can imagine reaching across the table for $2. And as you reach, you get one of the dollar bills, but the other one gets ripped as you pull it back across the table. And as a result, you destroyed some value, but the value that's left goes to you. So selfishly, it was worth it. And so if both people choose the defect or grab action, then they have $1 each. If they leave the money alone, they have $2 each. And if one person grabs and the other person just sits there, then that person who grabs ends up with $3. So that's the prisoner's dilemma. And usually people think about how, the interesting thing about the prisoner's dilemma is that no matter what the other person does, selfishly for you, it's better to grab. In a lot of cooperative situations, it's not like that. It's like if, in like a company hiring you to do a job, that's a cooperation. And it's worth it for you to go in if it's worth it. It's worth it for them to hire you, and it's worth it for you to go in, and you both benefit from that. And if they're not going to pay you, then it's not worth it for you to be there. That's like a more of a defect situation. But that's not what the prisoner's dilemma is like. The prisoner's dilemma is a situation where if your opponent cooperates, it's better for you to steal their money because you get more. And if they defect, it's better for you to steal their money because you get more. So no matter what they do, you're better off defecting. So this produces a very strong kind of equilibrium towards defection in the prisoner's dilemma. And nonetheless, real people sometimes cooperate in prisoner's dilemma-like situations. And so there's been a lot of research trying to understand how that works. And a lot of the literature on prisoner's dilemma focuses on repeated prisoner's dilemmas. The idea being that if you're going to play a lot of prisoner's dilemmas in a row, you want to have a reputation as someone who cooperates, so that other people will be willing to enter prisoner's dilemmas with you and cooperate, or so that they'll reciprocate the cooperation if they're doing some kind of tit for tat strategy. And that's not what I'm going to talk about. I'm talking about something else. I'm talking about prisoner's dilemmas where there's only one shot in the game, really, truly just one shot. And the difference that I'm going to introduce is that I'm going to suppose that the agents playing the game or the players playing the game are computer programs that can read each other's source codes completely. So, anything on a blockchain is like this unless it's encrypted. So smart contracts are programs that just can read the source codes of other smart contracts. And I think this is going to be a really important thing to understand technologically eventually. But it's also a sort of an analogy for the way human institutions can read each other's bylaws, or have a company social and actually meet the people that the company is composed of, so that you have some degree of mutual transparency between human institutions. Really, my motivation for this research is that in classical game theory, you pretend that the agents have this completely private way of thinking. They think about what the best strategy is, and they come out and they play it on the board. And then in open source game theory, which is kind of the opposite of classical game theory in this way, the agents are completely transparent to each other. Their source code is completely available, and if there's enough compute, you can just simulate them. And the real world is somewhere in between. Humans can look each other in the eye and have some sense of what each other is thinking or feeling. Human institutions can read bylaws and have meetings, et cetera, et cetera. So the reason I'm exploring this extreme case is not just because it really exists in the smart contract space, but because I'm just trying to flesh out this full spectrum of possibilities. And then most things in the real world are going to be somewhere in the middle of, perfect opacity and perfect transparency. Bush thought Putin was open source. Maybe. Or you thought Bush thought Putin was open source. So let's look at some really basic examples of open source prisoner's dilemma bots. And I've written these in Python, and I'm going to pretend like some of these Python functions already exist, but I haven't implemented them. The first one is Cooperate Bot. So Cooperate Bot is a very simple program. It takes as input its opponent's source code. So up here is a string. That's the source code of the opponent. And Cooperate Bot is kind of stupid. It just kind of ignores who the opponent is and returns cooperate, no matter who the opponent is. Defect Bot is maybe slightly less stupid than Cooperate Bot, depending on your morality, maybe slightly more stupid. But it thinks exactly as hard as Cooperate Bot. It doesn't look at who the opponent is at all. It just returns defect no matter what. So that's CB for Cooperate Bot, or DB for Defect Bot. Now let's look at some more interesting bots, and I'm going to ask you guys to actually think about this. So I'd like to actually switch to video soon for whoever's willing. I imagine some people are busy parallel processing other stuff, but I'd like to switch to video where I can sort of poll the room and get sort of like shows of hands that say, okay, I've formed my opinion about this or that question that Andrew's asking, because I found that the only way to communicate this stuff really thoroughly is to get people to think about it themselves. So here goes. Here's QPod. QPod is a very simple proof searching agent. And here's what it does. QPod stands for Cooperate Unless Proof of Defection. And what QPod does is it looks at its opponent's source code, and then it searches. I'll describe the search in a bit, but it searches for a mathematical proof using logic of the statement that the opponent when faced with QPod, is going to return defect. So I'm kind of abusing notation here because up here is a string, but now here really I'm evaluating that source code on this input and getting a defection. And if that proof search returns true, meaning that the QPod finds affirmative guaranteed proof that the opponent is going to defect against it, then QPod returns defect. Otherwise, QPod returns cooperate. And this otherwise here means that, it searched for a long time, it didn't find a proof, it gave up and returned C. And just to be extra clear about what the proof search process is, I've written a comment here describing a very simple procedure. I chose this procedure just because it's simpler to think about. You can imagine the proof search works by looking at every string that's less than or equal to some constant length. Here I wrote k equals 1 trillion. So for every string of length less than or equal to 1 trillion, the proof search function looks at that string and says, is this string a valid mathematical proof that my opponent is going to defect? I'll say that again. It first looks at the string A, because A is the first string in the alphabetical listing, and it says, is that a valid mathematical proof that my opponent is cooperating? Well, it's not a proof at all. It's not even a sentence. It's just the letter A. No. All right, next string, letter B. Is that a proof? No. Okay, so that eventually it looks at the string AA, then AB, then AC. None of that is a proof. Eventually, it looks at some pretty long strings. Like it might look at a string that's long enough that's actually a proof of the Pythagorean theorem, written out in purely algebraic terms. And that is not a proof of defection. So it keeps looking. And eventually, maybe it finds a valid mathematical proof that argues, based on whoever its opponent is, it argues using pure logic that the opponent is going to defect. And once it finds that, it stops the search. And then it returns a defect. But if it doesn't find that, it just keeps searching until it hits this length bound. And once it's looked at the string z, 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 1 trillion z's, and hasn't found a proof of defection, it just stops and says, okay, fine. Apparently this thing doesn't have a short proof of defection, so I give up. I'm going to cooperate. So that's my description of QPod. And DUPOC is the opposite. DUPOC is searching for a proof of cooperation. If it finds a proof of cooperation, if it finds a guarantee, logical mathematical guarantee that the opponent is going to cooperate, then it returns C. And then if it finds no such proof of length less than or equal to 1 million, it gives up and returns D for defect. And for some reason, my slides are like flashing forward. So I want to get you guys to think about this. What is QPod of DefectBot? And I guess it's fine if you saw some of the forward slides. But give me a wave with your hand when you form an opinion as to what QPod K of DefectBot is. And right now I can see a representative sample of 1, 2, 3, 4, 5, 6 video screens. And I'll just sort of, you guys are going to get the best treatment here because the presentation is going to be customized to your faces. So what is QPod of DefectBot? Wave a hand when you like have thought about it. All right, I think I have everybody. So the answer is, of course, that it depends a bit on K. So if you didn't think of how big K is, that's my first thing I want to communicate to you is like, hey, don't forget to think about how big K is, because if K is tiny, if let's say K was 5, you wouldn't have enough space to write a proof about anything. 5 characters is just not much space to write anything. So if K is very small, then you can't write any proof about defect-bot. So in particular, you wouldn't find a proof of defection. So QPod 5 of defect-bot would be C. However, in this case, I asked you about the case where K is a trillion, and hopefully you thought about that number, a trillion, at some point and realized, yeah, a trillion is enough to write a proof. And if you didn't have that, that's the first thing I need to communicate to you. Don't forget to think about how much space and time this agent has to think. That agents are affected by how much space and time they have to think. What they choose is a function of how much space and time they have to think. And I'm trying to capture that here a little bit with the proof length bound. Okay. So thank you for thinking about that. So now let's look at the next one. What is QPod of cooperate bot? And please just take 20 to 30 seconds to think about it and give me a wave with your hand when you have an opinion about what QPod K of cooperate bot is. All right, that's most of the waves. Okay. So thank you for doing that thinking. So the answer for cooperate bot is, it's a bit easier. Cooperate bot never defects. So no matter what K is, if K is small or K is big, you're never going to find a proof that cooperate bot defects. Does that make sense? So now here's an interesting thing to think about. How long does this program run? When you run QPod on cooperate bot, does it run? Raise your hand high if it runs for a long time, and low if it runs for a short time. Cool. I see hands going up. It's like crypto prices. Yeah. So this thing runs for a long time. Now we can think about it for a very short time and tell what it's going to do. We can say, okay, there's no, cooperate bot never defects. So QPod will never find a proof that cooperate bot defects, but it's going to look for a long time. Because if you look at how it's written, all right, I didn't say, figure out what your opponent does and make a decision. I said, search for a proof of defection forever until you hit a trillion, and then stop if you haven't found it. So the way, right, this is we're not talking about an arbitrary way of deciding whether to cooperate or defect. We're talking about this particular procedure, and this procedure is just going to keep searching and searching for a proof of defection until it hits this length band of a trillion. And that's like ASCII to the power of a trillion strings that it has to look at. So that's a long time. So that's a second thing I want to communicate to everybody, is that just because an agent is simple and you can tell what it's going to do doesn't mean its thoughts are simple. Its thoughts can be very long and protracted. Question. Yeah.
So if you're truly looking through all strings up to sort of like Library of Babel, all strings up to a length of trillion, wouldn't the sort of that op QPod of K equal D show up in that set of strings?
Yeah. So yeah, right. So that string would show up. In fact, once you got up to length, whatever it is, 15 or something, that there will be a string there that says op QPod K equals D. Yeah.
And there would also be one that says equals C.
And there'd also be one that says equals catfish.
Yeah.
Yeah. Yep.
So
that's right.
How then is QPod sort of determining like what the proof is? Because if a straightforward sort of assessment that like it is going to defect is not enough to sort of be a logical proof.
Oh,
what is the meaning there?
Yeah, cool, great. So I'm glad you asked me that, because without that information, the rest of the talk won't make sense. And that's part of why I have these questions here. So thank you. So a statement is different from a proof. Like here's a statement. Donald Trump is the Queen of Mars. Okay. Have I convinced you that Donald Trump is the Queen of Mars? No, right? I would have to say a lot more to convince you of that. And maybe no amount of talking could convince you. Now, mathematical statements are the same. I could say, the square root of 9 is irrational. I could write that down as a statement. Is that a proof that the square root of 9 is irrational? No. Think back, to your homework when you had to prove something was irrational, if you did that in college, or if you ever had to prove anything, right? You write the answer at the bottom of the page. I'm supposed to end this argument by saying the square root of, let's say it's square root of 2 is irrational, right? You write that at the bottom of the page, and then you try to start from basic principles that like 1 + 1 = 2 or whatever, until you get from basic assumptions to the conclusion. So this is the definition of a formal system of proof in math. The way it works is as follows. I'm now just going to give you the complete definition of what a formal system of proof is. It's a few things. The first datum is a list of axioms, which are some strings that we think of as representing statements that we just believe without having to have proofs of them. And so you could imagine in piano arithmetic, the usual basic system of proof that's used to prove things about arithmetic or numbers or number theory. The axioms look like things like there is a number called 0. It's a statement that says 0 exists. That's the first statement. If you know that there exists symbol, that's like a backwards E, and then there's a 0. And then the next another axiom is, there's this operation S for successor, which means the number after. So then you can say there exists successor for any number X, or for all X, there exists successor X, which means for any number, there's a number after that number. And so there's a few very, very basic principles like this that you write down. Those are called axioms. And that's the first chunk of what makes a formal system of proof in math, is a list of axioms. The second chunk of what defines a formal system of proof is what's called rules of inference. So a rule of inference is just a rule for looking at a list of statements you believe and pulling out, then writing down a new statement that you believe as a consequence of the previous ones. And for simplicity, I'll just tell you what the two rules of inference, there's only two that you need in piano arithmetic. First one is called Modus Ponens, which is if you believe in a statement of the form A and you believe in a statement of the form A implies B, then there's a rule that says you're now allowed to believe B. That's called Modus Ponens. Whenever you have in your list of statements anywhere above you on the page when you're doing your homework, if you've got an A and you've got an A implies B, you're now allowed to write down a B. So that's the Modus Ponens operation. The second operation you're allowed to do is called specialization. So that means if you believe at some point in your homework, you get to the point where you say, for all X, property of X is true. So maybe for all X, X plus 2 exists. All right. Once you get that belief, you're allowed to say, in particular, 17 plus 2 exists. So that's called specialization. Whenever you believe a statement about all objects, you're then allowed to write down any special case of that statement for any particular object. So if you believe all numbers, for all X, X plus 2 exists, you're certainly allowed to believe that 17 plus 2 exists. So those are the two rules of inference that make up the rules of predicate logic, and is what you need to prove pretty much everything we know about arithmetic. We just have these pretty basic facts about like the existence of 0 and plus. And then we have these rules that allow you to do very basic logic. A implies A implies B, therefore B, or for all X, P of X, therefore P of Y. And so a proof that coming back to your question now, Michael, a proof that op of Q pod K equals D is going to start with a bunch of definitions at the top of like what Q pod is, Q pod equals, and then like a big formula defining what Q pod is. And it's basically this source code, but you'd have to like write it down. You'd have to do some work to represent it in arithmetic mode if you're using arithmetic type proofs. And so you start with that definition, and then you just write down basic axioms of math and then apply logic until you end up with a statement at the end that says opponent of Q pod equals defect. So a proof is just pretty long, depending on how complicated it is to prove. It could be very long, it could be very short. Like if you've heard of Fermat's last theorem, famously, this was a proof that started with basic principles, and Andrew Wiles wrote down more and more things. He used more advanced rules of inference that mathematicians could do in their head because they know how to derive those rules from the simpler rules. So he didn't use just the two very simple rules that I described, Modus Ponens and specialization because, we allow him to skip steps on his homework because he's a professor at Princeton. But in theory, every time he skipped a step, you should be able to fill in all the little modus ponens and specialization steps in between. So in theory, his proof of Fairmont's last theorem can be expanded out into a longer proof that just only uses modus ponens and specialization as the logical operations. And that's the type of proof that I'm imagining looking for here, of the statement op of qpod equals defect. Okay, that's my explanation of what proofs are. Questions about it, because I do want you to understand there's no point in going on unless it starts to make at least some amount of intuitive sense. If it doesn't make complete sense, that's okay, but please do probe a little bit more if you have questions about it.
I have another question. Is there a way to upper bound the length of a proof based on the length of the program that the proof is about?
Sometimes. There's not a fully general way to do that because of the halting problem. You could imagine asking the question, does this program halt? And if you could always answer that, then you'd solve the halting problem, which you can't do. And in fact, you can prove Gödel's incompleteness theorems using the unsolvability of the halting problem in the way that I just described. So no, but there are certain programs that you can look at and you say, yeah, that's going to halt. For example, this program is definitely going to halt. Why? Well, you can bound how long it's going to run. So you can prove that this program is going to halt, and sometimes you can prove that a program is going to halt and return a certain result. If I just wrote while k less than a trillion, wait, and then return 5, you can prove that that's going to run for a long time and return 5, and you don't have to run it. And in a sense, that's what compilers are doing all the time. Whenever you write this like sloppy human readable source code, the compiler transforms that down into a simpler thing that's going to run faster. And it's using, if it's a good compiler, which most real world compilers are, it's using principles that are formally verified in advance that, this simplification is not going to alter the behavior of the program. So you really know that this compiled version is going to do what the source code version describes. So certainly there are lots of operations that are going to run for a long time, but you can write a proof in advance about how it's going to end. You just can't always do that. Otherwise you solve the halting problem. So this is, I'm using this very simple notion of proof because it's the simplest notion. There are more complex notions, but we just won't bother with them because this is a thought experiment and we want it to be simple. And I've asked about qpod here, and coming back to the main thread of the talk, we can see that qpod returns. This is a typo. We should be talking about qpod of cooperate bot. Qpod of cooperate bot does return C, and the reason. Let's think about the reason. Is it because there's a proof that cooperate bot cooperates, or is it because there's no proof the cooperate bot defects? And I'm just going to fix this typo right now, just in case it's confusing people. There's visual learner type people in the audience. It's just going to be confusing. So I'm going to fix that. And here we're back. So here's cooperate bot. I'm telling you, it returns C as you no doubt guessed. And it's important to notice that it doesn't return C because cooperate bot cooperates. It returns C because there's no proof that it defects. And those are very related statements, but sometimes things are true and you can't prove them. The halting of certain programs, they halt, but you can't prove that they halt because they're set up in such a way to confuse your proof system. No matter what kind of proof you try to write, the program reasons about that proof and makes it not work out. So there are things that are true that can't be proven. And so it's not the same to say, that cooperate bot cooperates versus there's a proof of it versus there's a proof of defection. So we do have to think about the difference between truth and provability. And similarly, we have to think about the difference between provability and provability in a short proof that's, only uses 1,000 characters or 1,000,000 characters or a trillion. because that affects what a bounded computer system is able to figure out. If the proof is very, very long, it can't figure it out because it's too long. So this is just a warm up to get you thinking about these differences between truth and provability, difference between having a proof and having a short proof. And now I'm going to get you to think about the first more interesting, I guess this is the first case where you're going to have two things proving stuff about each other. So we're going to say, let's just take K as a trillion, and I'm going to ask you to think about what happens when QPod faces QPod. So here op is equal to QPod, and you can try thinking this through. And I just want you to take a minute. And if people are willing to talk about it with me and each other, that's the best, because this can be confusing stuff and it's good to talk it through. So let's just take an entire minute to just form an opinion about whether you think QPod is going to return D or return C. Give me a wave if anyone who's formed an opinion, like I think I have an opinion that it's going to return C or D, and you don't have to be sure, it's okay, but just like all right, let's give another 30 seconds for a couple more opinions to form. All right, so I'd like you guys to, let's do this in a principled way. Let's say D is higher in the alphabet than C. So D is going to be hand at the top of the screen and C is going to be hand at the bottom of the screen. So if you're willing to reveal, just reveal if you think QPod is going to return defect at the top of the screen or cooperate at the bottom of the screen. Go. All right, I see cooperate, and question mark. Cool. So for the folks who said cooperate, why is it going to return cooperate? And you don't have to know for sure, but just give us your intuition and just pipe up.
I'm outside and it's kind of loud.
I can hear it's not. There's no background noise for me. Please do.
Okay, great. So it's self-referential. So it's not gonna, what it does, what it thinks the other bot is gonna do depends on what it thinks itself is gonna do. So it's gonna run out of time because it can't, prove it one way or another. And then because it didn't find a proof of defection, it's gonna cooperate.
I saw one face nodding. Is it Dwarkesh? Did I say that name correctly?
Yeah, I agree.
Yeah, and is it for the same reason? You have same conclusion for the same reasons, Al? Do people have different opinions? No, I agree, but for a different reason, or I don't actually know, or dissenting views. I kind of want to hear those, if possible.
I thought the same as Alan.
You thought the same, Michael? Is it Carola?
Yeah, I didn't think it would find proof of defection, but now I'm realizing there is no scenario where it just runs forever. It actually has to terminate once it gets through all strings of length less than or equal to K. So yeah.
I see. So you're where are you at now in terms of C or D?
I think it would cooperate. I think it would return C. But...
Got it. Cool. So guys, thank you for using your brain cycles to think about this, because I've experimented with different ways of doing this presentation, and it really only works if people think. So thank you. And because you've thought about it, you've now loaded a bunch of concepts into your head. Okay, how long is it going to run? How long is the proof? Does it find the proof? All that stuff. That's key. And you're thinking all the right thoughts. Certainly, if K was tiny, it's important to notice that you would get C. If K was 5, of course you get cooperation, because it would prove nothing. You couldn't prove anything at all. In particular, you couldn't prove defection, so you get C. But we're thinking about a trillion, this one has another typo. I wrote Dupac instead of QPod, so this top part here is a typo. But down here, you guys have noticed it's a little bit circular, right? It's QPod of QPod is going to be defect if QPod of QPod can prove that QPod of QPod is going to be defect. And it seems like a circular definition. And you can't prove, in order to prove that QPod cooperates with QPod, you have to prove that QPod proves that QPod cooperates with QPod, which means you have to prove that QPod proves that QPod proves that QPod cooperates with QPod, etc. So this feels kind of like an infinite regress or a Stack Overflow type situation. I'll say that about 95% of people in computer science or math, eventually give them a little bit of time to think about it, manage to converge on this understanding, which is wrong. This one's not a typo. It's not true that it cooperates. It defects. QPod of QPod is defect. For redundancy, QPod of QPod is defect. And it's weird. And I hope you believe me now that open source game theory is weird. The reason is because there's a generalization of Gödel's theorem that I proved in 2019 that uses a result called Loeb's. It's a generalization of so Loeb's theorem generalizes Gödel's theorem, and then my result generalizes Loeb's theorem to work for computers with bounded resources, and it shows that they defect. And I'm going to spend the rest of the talk sort of elaborating on that and what that means for the world, because it's weird. Interestingly, other people sort of conjectured this based on Loeb's theorem, but Loeb's theorem uses infinite compute in the sense that the proof searches or the proof existence statements don't have any bounds on how long the proofs are or how hard they are to find. And so when people conjectured that these things would defect, I thought, well, that's just infinity being weird. The weirdness is coming from infinity. I'm going to look at finite computational resources, and I'm going to show that with finite resources, you don't get any of the weirdness. But spending a month trying to disprove the conjecture, I couldn't do it. I couldn't prove them wrong. So then I switched to, I guess I should dutifully try to prove them right now. And that took 3 months, but it worked out. So here's basically the idea. There's a theorem called Loeb's theorem. I'm just going to, because I only have 15 minutes, I'm going to try and think if there's a simpler way. I think there's a simpler way I can summarize how this works that is a little bit less accurate, but it's probably good enough. The basic idea is that you can write a proof that contains inside of itself something like a compressed version of itself. So it's kind of like, I'm just going to mock this together on like a sticky note on the Mac. And I'll share that now. Let's see, sticky note. All right, you guys see a big yellow sticky note? So here's kind of how the proof, this is like kind of how it works. And I'm working on making it work more like this so that this narrative will be more true. But it's roughly like this. You have a proof that says, like chapter 1 of the proof, it's pretty long, but chapter 1, it has this sort of like compressed version, like some kind of compressed hex string inside it. And it says that super compressed hex string is a compression of a valid mathematical proof that QPod of QPod is defect. I'm leaving out the K. And it just spends a long time, first showing that this compressed thing is actually a valid mathematical proof, and then showing that the last line of the proof is D. But it does so from the outside using kind of like analyzing the zip file. It's like a zip file, kind of analyzing it from the outside. And then chapter 2 says, chapter 2 is much shorter. Therefore, a proof of defection exists. I'm just writing D for the statement QPod of QPod equals D. Chapter 3 says, notice that proof of D exists implies D, because they'll find the proof and cooperate. In fact, I'm going to say short proof. Short means, less than a trillion. And then, so short means length less than or equal to a trillion. And chapter 3 says, notice that short proof of D exists implies that D will happen because the agents will find that proof and defect. And then chapter 4 says, by 2 and 3, defection, modus ponens. So I'll just kind of work through that again. You've got this sort of compressed proof of defection. You analyze that and verify that it's a valid proof and it's a proof of defection. Then you have a conclusion. Okay, a proof exists. If we were to unzip this string, it would unzip into a proof. By the way, this string, when you unzip it, unzips into this document. That's the key, is that you've cleverly constructed this fixed point situation where this string is the WinRAR or the WinZip of this document. And that's quite tricky to do, but there's a way of doing it in the type of compression that you use is structured enough that you can do that. So you can cook up this document with the property that it contains a compressed representation of itself. And then it analyzed that compressed representation to confirm that it is a compression of a valid proof. And if you have a compression of a valid proof, then that means that the proof exists. And then that means the agents, the players will find it. And that will cause them to defect. And that lo and behold, the proof is valid because it's kind of, the whole thing is self-referential, but the proof turns out to be valid because you look at the steps and you're like, yeah, those are all valid steps. And it manages to refer to itself. So by knowing about its own existence, the proof turns out to be valid. Okay, Dwarkesh. Or Dorkesh.
Yeah, so doesn't this still require infinite computation, because you had to unzip that proof and then you had to unzip that proof to figure out if that's valid?
No, I made it. I just made it by hand. I worked out, you can read the paper. There's just this proof and it contains these steps inside it that are sort of like a mirror of the larger proof. So it's like let me go back to my browser. If you've ever seen a Quine is a program that prints its own source code. And it does so by sort of containing a recipe for how to reconstruct itself. So let me share that. So here's a program in Java that prints its own source code. It's pretty cool. It's a functional program. It doesn't write anything to disk. It's basically got this header, and then it has a quoted version of the header here, cleverly put together into a bunch of strings. Then it has a quoted version of the footer, and then it has the actual footer of the program. And all the footer does is it just prints out, it sort of prints the quoted version of the header twice, once outside of the quotes and once inside the quotes. And then it prints the bottom once inside the quotes and once outside the quotes. So these instructions here are enough to use these building blocks here to reconstruct this entire program. And so this is, Michael has a question.
Yes. Can we go back to your sticky note?
Did you guys see did I successfully share the Quine program?
Yeah.
When I was highlighting? Okay, cool. Let's look at the sticky note. Yeah, sticky note.
So couldn't I also assert that there's a compression of a valid mathematical proof that qpot of qpot is C, that is incompatible with C?
Yes, great. So you could try and do that. but it wouldn't work because you try to get here. A short proof of C does not cause the programs to cooperate because they're not looking for a proof of C. They're looking for a proof of D. So it would break at chapter 3. This is the step that doesn't work. Q-pods are looking for a proof of defection. If they find a proof of defection, they're going to defect. If they find a proof of cooperation, they're going to be like, oh, interesting, a proof of cooperation, and then keep searching for a proof of defection. And so it's not the case that short proofs of cooperation cause cooperation. But it's the case that short proofs of defection cause defection.
But isn't a short proof of cooperation sort of mutually incompatible with a short proof of defection?
Yeah. So, but you're talking in a hypothetical, right? So whenever you do a proof by contradiction in math, you imagine some crazy hypothetical. Like imagine if square root of 2 was rational. Let's say it is rational, and you write down, root 2 equals P over Q, and then you do some math and you show that P and Q have to be both even and odd, and you're like, that's crazy. So then you say root 2 has to be irrational. It's important that these. It's important to be able to consider contradictory scenarios in math and work out what would happen and then discard them. And so it's you and I are considering scenarios where QPod finds a proof of cooperation, but of course that won't happen. Now, why won't it happen? Well, because they're going to defect. You're posing a hypothetical. Michael is saying to Andrew, why couldn't this work out? And I'm saying it won't work because this step wouldn't work out. Now, this is all still hypothetical. None of it's going to happen because what's really going to happen is they're going to defect because there's a proof of defection and they're going to find it. I don't know. It's not that satisfying. Yeah, Dorkesh?
Yeah, so this is, you're probably going to answer this anyway, but so can you just give me, because the default behavior of this is to cooperate if it doesn't find the proof of defection, right?
Yeah.
So then where does the defection even come from? Like, how can you even, can you give me an intuition for that?
It comes from the existence of this self-referential proof. Like this self-referential proof of defection exists. And it exists because of the structure of the program. The program is structured in a way that it's going to defect upon finding a proof of defection. It's kind of like the program is designed to make self-fulfilling prophecies of defection successfully self-fulfill. And if you design something to help self-fulfilling prophecies come true, then they come true. That's part of the philosophical takeaway here is that if you set up a system where it's standing ready to self-fulfill, to help a self-fulfilling prophecy come true, then that self-fulfilling prophecy can come true, and will come true once the program or its system has enough time to conceive of the self-fulfilling prophecy. It'll have the idea and then it'll self-fulfill. I'm sorry, Alan has a question.
Yeah. So I get that if it finds a proof of anything, it's going to defect, right? And so you can sort of set up this trivial sort of self-referential proof of anything. And if it's going to be a proof of something, it has to be of defection.
No, it's looking for a proof of defection. So
yeah. Well, if that proof is going to cause anything to happen, it has to be a proof of defection.
Okay.
Not right, but it feels like there has to be a maximum amount that you can compress a proof in this system. It kind of feels like if you, it sort of feels like, I don't know, if I'm not sure how to express the kind of what I'm thinking of, but it feels like there has to be a maximally, like you said, it's looking for a proof of defection. And it feels like there has to be a maximal compression of a proof that is still valid, right? And it's if you
still, yeah, so there's compressing it in a way that's still valid, but then there's compressing it in a way where you can tell that it would be valid if you decompressed it. And that's really what what's going on here. It's like there's this thing, and you're like, if we decompressed it, it would be valid.
Sure.
Which is different from saying it's a valid proof. It's like Andrew Wiles's proof of Fairmont's last theorem. If you decompressed it, it would be valid, but it's not valid. It's not a perfectly logically valid proof yet because we haven't filled in all the steps that he skipped on his homework.
And you can just sort of do that as many steps as you want in like finite with like a finite k.
So k has to be big enough. So you can't. I think my estimate is k has to be at least like 10,000. But I'm not super confident that I'm quite confident that 1 million is big enough, and 1 trillion is like way more than big enough. So you can't get k equals 1 or k equals 1,000 to work. But once you get around k equals 1 million, you have enough space to write down the apparatus for compressing and decompressing the proof, and then with that you can determine that this thing is going to decompress into a proof of defection, and then from there you conclude defection, and then defection, the self-fulfilling prophecy, self-fulfills.
Okay, that makes more sense. Okay, thanks.
So I'd love to give like a whole lecture series on this, but I've been allotted an hour. I guess where I'll leave is, I can come back and we can talk more about this, or you can reach out to me at my Berkeley email address or my work email address, and we can talk more about it. But I think the physical possibility of systems, not just systems, but arguments that are aware of their own existence, such that I don't mean arguments about systems that are aware of the system's existence. I mean an argument that is aware of the argument's own existence. That's how these proofs look. And when you discover one of these arguments, it can change your plans. And that's what's happening here with the QPods. They're discovering a self-aware proof of defection and defecting on that basis. But the upshot is you can make DUPOC, which cooperates for self-fulfilling reasons and is completely unexploitable in the prisoner's lemma. You can never screw over a DUPOC because it will never cooperate with you unless it knows you're going to cooperate. So it's like there's this really robust, you can imagine an ecosystem of these DUPOCs going around, and they seem kind of standoffish. They're not going to cooperate with you unless they know you're going to cooperate. But if you're following a similar principle, a self-fulfilling cooperation prophecy comes true and you end up cooperating. But if you're a jerk, it never proves that you're a good person because it can't, because you're a jerk, and then it doesn't get exploited by you. So to me, it's very exciting population dynamics to be played with here. But I feel like I should stop and hand back to Jonathan to close out or whatever. I'm not in a rush to go, but I'm sure you guys have schedules. So Jonathan, back to you. Thanks.
Yeah, I mean, we can do a quick show of hands if folks can and want to stay. I love the idea of doing a part 2 if if you do want to schedule something for a month or a few weeks or a few months or whatever to come back. Do folks want to take another 10 minutes and keep diving into this? Yes. Okay, let's do that. Let's set I'll keep my eye on the clock and we'll wrap it up in about 8 to 10 minutes. But yeah, it looks like Dwarkesh, were you just voting to stay or did you have a follow-up question? Or it sounds like that's okay with you, Andrew, to take another.
Yeah,
10
totally.
so.
Yeah.
Okay.
I'm free till 11:30. So.
Okay, great.
Yeah.
Bye, Red.
I didn't know a specific question. I guess one thing, because you like build smart contracts with this kind of where they can analyze each other's code.
Yeah. So there's a whole continuum of like metaphors that you can look at that aren't purely open source yet, but that are kind of open source. And in a way, a multi-sig contract, you can sort of see it as a metaphor for, you can use this as a metaphor for a multi-sig contract, in a sense that once the multi-sig contract is out there, you can think of it, this is a metaphor now. This is not real, like, perfect mapping, but metaphorically, once the multi-sig contract is out there, it's kind of searching for a proof of cooperation in the sense that if ever your digital signature and my digital signature appears on it, it will be like, boom, proof of cooperation has been found. And then it starts on the basis of a proof of cooperation having been found, it then executes the cooperation, which is the thing that we wanted it to do. So you can think of a multi-sig contract as a DUPOC, sort of like a DUPOC. But it does so just based on your identity rather than your source code, right? Like it uses your signature, which is a tracker of your identity, or it's a reputation that you've established. Your digital signature is just a reputation. You could imagine contracts that require not only your digital signature but some kind of proof of source code, rather than a proof of having a private key. And I suspect that in the long run, blockchain based commerce will use some amount of mutual transparency among smart contracts. Like you're going to have smart contracts that are encrypted that don't reveal their secrets for how they work, but there's going to be other smart contracts that aren't. And then eventually we'll get to a point where we have smart contracts that look through another smart contract and be like, is that a reasonable smart contract? And then so smart contract A reads through smart contract B and goes, is that reasonable? And B looks at A and says, is that reasonable? And you could imagine them getting into a stalemate where A is like, well, I would be reasonable if B were going to be reasonable. And B is like, I would be reasonable if A were going to be reasonable. But there's a way of setting them up. If they're open to these self-fulfilling prophecies of reasonableness, then you can set them up so that they'll then collapse into a sort of reasonableness state. So that excites me. I think it's a few generations of like, not necessarily human generations, but tech generations away from being like realizable and useful. But I think it's going to be. I think it seems like a thing both to aim for and to be ready for.
And another question.
Yep.
So this all hinges on K being reasonable, and I think sort of Alan was alluding to this a little bit as well. Does that mean that the behavior inverts if K is like unreasonably short?
Yeah. If the smart contracts in the metaphor don't have enough time to think about each other, they'll just fall back to their default behavior for what they would do if they don't finish thinking. So there's in my paper, I showed this more robust theorem that goes beyond DUPOC. It just defines a certain principle of fairness, and you can be like DUPOC is sort of fairness only. It's just like the only thing it thinks about is reciprocation. It tries to prove that you're going to cooperate, and if so, it cooperates with you. It's the opposite of QPOD. QPOD thinks only of punishment. DUPOC thinks only of cooperation, and if it finds that, it does it. And I'll get to you in a second, Carol. Thanks. So you could imagine, other versions that it's like, I'll cooperate with you if you cooperate, or if your name starts with M, because I like people whose name starts with M, and I'll cooperate with them even if they're defectors. You can imagine variants of DUPOC who have additional criteria for cooperate, or like, I'll cooperate with you if you're a cooperator or if you're my kid. Even if you're a jerk to me, I'll still be nice. As long as you have this fairness clause inside you, which is that, like with DUPOC, provable cooperation of the opponent is necessary for DUPOC to cooperate. But imagine things where provable cooperation of the opponent is sufficient, and I call that being fair. And I can show that any two fair agents, if they're above a certain computational threshold where they have enough time basically to think about the theory I'm describing to you, which is what they have to do. The theory refers to itself and causes itself to be true. So they need enough time to load up some self-referential machinery and use it to verify the self-referential machinery, and then use that to verify each other. Then any two fair entities are going to cooperate with each other. And the cool thing is you can have massive imbalances of compute. Like once they're both above the basic compute threshold, here's the fairness result. You know, A sub k and B sub k are both agents that have some parameter k that determines how long to get to think. As long as A and B both have compute above some threshold R, they end up cooperating with each other. So A could be massively more compute endowed than B, but as long as they're both above the basic threshold of self-awareness, then they can do this self-fulfilling prophecy stuff, which we should make sure that we set it up so the self-fulfilling prophecy is a good one instead of a bad self-fulfilling prophecy. Most of my interest in this topic comes from being like, whoa, this is weird. Weird stuff can happen that we're not expecting. And I want to make sure that it's not a bad surprise. It's a good surprise. So sorry, Carol, I was long-winded in my answer to Michael's question.
Great. This has been really thought-provoking. And I'm still trying to wrap my head around the generalization of the Loeb's theorem. And I'm trying to understand it is what you're showing here the same thing as saying that any possible behavior of QPod or any of these bots exists as a proof, a compressible proof, somewhere in QPod's code. So if you can just audit the code.
The proof is not in the code. The proof is now you could
extracted.
Now that would be better. So you could actually make the proof search a lot more simpler. Instead of searching alphabetically through all possible strings for proof, you could just do something simpler, like look inside the program and see if it has a proof about itself. So that's what you just described is how QPods or rather how dupocs should be designed. They should contain inside themselves proofs about themselves. But that's not how I wrote it for the talk. It's not strictly speaking necessary for the code to contain the proof. The proof is just a mathematical object that you can find through thinking for a long time, rather than something that's written down already.
Right. So you have to be able to identify the possibility that the bot could defect under some conditions. That essentially is that the generalization of the proof idea here, or?
Yeah, you have to be able to identify. You have to be able to identify that. Let's look at dupoc, because QPod is kind of ends up being a jerk for self-fulfilling prophecy reasons, and dupoc ends up being nice for self-fulfilling prophecy reasons. So let's focus our attention there. Let's focus our search towards the good outcome. This K has to be large enough so that while it's running, it manages to declare enough space in memory to write down a self-fulfilling argument that its opponent is going to cooperate. And that proof is not, it ends up being written in memory, but not in the source code, right? So like the space that a program uses up when it's running is typically much more than the space it takes to write down the program, and because that's the memory usage. So so the proof ends up being written in memory, but not in the source code. It's kind of like your mind has a lot more information than your DNA. Like your DNA only has like a few megabytes, like maybe a couple hundred megabytes of information. I forget the exact number, but your mind has like all this video feed that you've seen for your whole life that you can remember information from. So programming you is like takes a much less space than running you. In the same way, programming dupoc just takes this small amount of space to like write down a proof search function or whatever, but then running it takes more space. So if you ever want to nerd out about this stuff, it's my whole shtick. So I'm always excited to talk more about it.
Our next talk is next week, April 27th at 1600 UTC, from Andreas Stuhlmüller, co-founder of Ought, a nonprofit doing research on using machine learning to support deliberation. The talk title is Automating Reasoning About the Future, Language Models as Research Tools. For those of you watching on YouTube, please do like and share this video, and also hit the subscribe button. If you want the Zoom link to join future talks, you can join our mailing list in the footer at research.protocol.ai. Thanks for joining. We will see you all next time.